In these series of videos, we're going to look at the science and principles knowledge gained in the classroom, helping us work towards our level 1 and level 2 exams, but also as an intro to our level 3 science and principles as well. First, we looked at SI units, and we looked at the SI units for the flow of electrons. The flow of electrons being the flow of current in a circuit, and current is measured in amps. We looked at potential, the difference in potential between two parts of an electrical circuit being the potential difference. Potential difference is measured in volts, as is EMF, electromotive force, generated at the terminals of a battery or generator set, has the potential to develop a voltage. Therefore, the EMF is also measured in volts. We've got frequency. Frequency is the number of cycles per second. And in the UK, our frequency of our AC waveform is 50 cycles per second. Weight, the one that always catches us out. Weight is measured in newtons because mass is measured in kilograms. And I've been beating on about that in the classroom. Hopefully we've nailed that one now. Resistance is the opposition to current flow and is measured in ohms. The rate of doing work is power and is measured in watts. Those are some of the many SI units we've looked at as we've gone through our studies. And if we're going to default to a position where we've got to remember a select few, they're probably the most important at this stage and to remember. But I'd like us to think that we can remember a vast amount more of the SI units as we go through, and the presentations will pick up other ones. We went on to look at our electron theory, and we said that everything is made up of molecules. Molecules are very small, but in turn they are made up of even smaller things, and those are atoms. We then looked at the basic construction of an atom, being a center nucleus containing protons, which are positively charged, and on the outside of the nucleus itself are electrons, and electrons are negatively charged. We suggested there were three states of matter, those three states being solid, liquid and gas, and depending on how well held together the molecules were within that substance made it a solid, a liquid or a gas. So if they're tightly bound, they'd be in a solid. If they're loosely bound, it would be a liquid. If they're free flowing, it would be in a gas. But the three states of matter are solid, liquid and gas. On the back of looking at the construction of an atom, to say that if a material had a free flowing electron in the outer shell of its construction, that it's likely to be one that can be a conductor. If they are tightly bound electrons, we said that is likely to be an insulator. We went on to look at the most common conductor material being copper, silver possibly being the best one used widely within the electrical industry, but not selected for cables due to the fact of its expense. We looked at insulating materials from paper to PVC, PVC standing for polyvinyl chloride, and we looked at other insulating materials such as magnesium oxide, used in mineral insulated copper covered cables as well. We suggested aluminium could be used as an alternative to copper, and the exam always likes to use aluminium as an alternative to copper based on the fact it's considerably lighter in weight, not quite as good a conductor as copper, but the exam tends to ask questions based around its construction being lighter than that of copper. We looked at using carbon as a semiconductor for things such as brushes on motors. When the brush themselves get hot through friction, they become a better conductor. We went on to expand our knowledge on EMF to a small degree when we looked at the three ways in which you can develop and maintain an EMF. Most obvious being chemically in a battery, at the terminals of a battery that can develop an EMF. We said magnetically, and we'll go on to look at the basic constructions of AC machines and DC machines by rotating a copper coil in a magnetic field, so we can produce and develop an EMF magnetically. And thermally, in the form of a thermocoupler. Two dissimilar materials joined together end to end at vastly different temperatures can develop an EMF. The exam will often ask us what the three effects of electricity are. The three effects are chemical, magnetic and thermal. We looked in our electron theory notes in the classroom that a copper atom has a loosely held electron in the outer shell. This loosely held electron is negatively charged and is free to flow amongst the copper atoms. If we can cause this loosely bound, negatively charged electron to move in one direction through the material, in this case copper, we have the basic principles of current flow. In order for current to flow, we need to apply an EMF, an electromotive force, to the conductive material. And we saw in our previous presentation, that's caused in three ways: chemically, magnetically, or thermal. These electrons themselves are too small to quantify as individual electrons. we quantify them as a coulomb. When working out mathematical questions that requires us to find the coulomb, in other words, the transfer of electrons through a conductor, we need to use the formula Q for coulombs equals I for current times time in seconds. So to find coulombs in an exam question, we would use Q equals I times T, which we said also could be quit. Q equals I times T. We can use a triangle in order to work out the other two missing elements of Q equals I times T. We said that if we covered over the one we were looking for, mathematically we could work out the other one, whether it would be Q over T to find current, or Q over I in order to find time, and time being in seconds. After doing questions based on coulombs, Q equals I times T, and the formula to find current and time in seconds, we went on to look at the underpinning knowledge for Ohm's law. First of all, we looked at a basic circuit comprising of an EMF, conductive materials throughout the circuit, a fuse, a switch for control, and a load. In one of my other presentations, we looked at basic Ohm's law and basic simple circuits in order to find voltage, current, and resistance. The formula being V equals I times R. Sometimes people like to say Ohm's law is very interesting reading. V equals I times R. After we looked at those basic circuits comprising of a load, applied voltage, and a current in order to work out resistance, current, and voltage, we developed that on to look at series circuits with more than one resistive load. Our default position for the exam is to remember everything that I say, a nice position to be in. However, if we were only going to remember some elements of the underpinning knowledge for principles, this video presentation is trying to default us to that position, one where maybe a calculator isn't used, but knowledge can be answered within this section of the principles exam. So we said in a series circuit, the common element is current. So the current flows through the whole circuit and is common throughout. We said an ammeter is connected in series and is of very low resistance. Again, this question comes up in the section under Ohm's law. The total resistance in a series circuit is the sum of the individual resistors. If you had a resistance of 2 ohms, 5 ohms, and 10 ohms, the simple addition of 2 plus 5 plus 10, giving you 17 ohms for total resistance in a series circuit. Total voltage in a series circuit is the voltage that pairs across each individual resistor added together. We then moved on to look at parallel circuits. Parallel circuits are slightly more involved, but again, we're looking for a default position in order to answer some of those multi-choice questions. The common element in a parallel circuit is voltage. Voltage will appear across each of the loads exactly the same as the supply voltage. The total resistance in a parallel circuit is not as straightforward as simply adding them together. We looked at the formulas in the classroom, and again, I would expect you to try and remember those to get the higher level of pass, the distinction level of pass. Okay. However, this video presentation is to put us in a position where we get the required surface-based knowledge in order to pass the exam. So we need a default position. If we've got 2 resistors in parallel of the same value, say they're both 4 ohms, the total resistance in circuit is half of one of those resistors. In other words, 2 ohms. 2 10 ohm resistors connected in parallel, the total resistance will be 5 ohms. If we have 3 resistors connected in parallel, they're all of say 9 ohms each, the total resistance in that circuit would be 3 ohms. In other words, a third of one of the resistors. And we can see how this pattern moves on as we go to 4, etc. Another one worth remembering on parallel resistors is we have a 200 ohm resistor, a 200 ohm resistor, and a 1 ohm resistor connected in parallel. The total resistance in circuit is less than 1 ohm. We are heading towards a multi-choice exam that may give you answers with only one resistor value less than the smallest one of those connected in parallel. No need to work it out, no need to get a calculator out and start working ourselves through more complicated sums. The answer will be less than the smallest resistor in circuit. Great position to be in. Another formula that makes the total resistance of 2 resistors connected in parallel more simple is the one where it's product over sum. In other words, we take the 2 resistor values and multiply them together, and we put it over the 2 resistors added together, and therefore work the calculation out for the total resistance in that circuit. We also looked at connecting a voltmeter in a circuit. A voltmeter in a circuit is connected in parallel, and is of very high resistance. This is a whistle-stop tour of Ohm's law and is the minimum requirement of knowledge heading into our Christmas exams. However, we'd expect to have a deeper, more understanding knowledge of the section that we're in on Ohm's law. However, this is what we need to fall back onto. Fault position is to remember those key elements that I've just mentioned in this. After recapping our Ohm's law notes, we went on to look at resistance and resistivity, and we said the resistance of a conductor will be affected by the length of the conductor. Longer conductors have higher resistance, so shorter conductors have less resistance. The cross-sectional area will affect the resistance of a cable. The bigger the cross-sectional area, the less the resistance. The smaller the cross-sectional area, the higher the resistance. Temperature also will affect the resistance of a cable. The hotter the cable, the higher the resistance. The exception to this rule is carbon, being a semiconductor, which we know from previous presentations works in the opposite way around. In other words, the hotter the carbon becomes, the better a conductor it becomes, therefore the resistance is lowered. As well as looking at length, temperature and area affecting a conductor's resistance, we also looked at its resistivity. And we said silver has a lower resistivity than copper, therefore is a better conductor. And aluminium has a higher resistivity than that of copper and silver, therefore is not as good a conductor as the other two. However, all three are widely used for different applications within the electrical industry, with copper being the most common material used in conductors. We went on to work out the resistance of a conductor by using the formula resistance equals the resistivity multiplied by the length divided by the area. In other words, resistance equals rho L over A. Again, these video presentations are to put us in the position where we get the amount of knowledge required to go into the exam where a calculator wouldn't be used. Remembering the formula resistance is rho L over A is a good way of getting marks within this section. I'd like to think that we can apply that formula and rearrange it to find three others, whether it be length, resistivity or area. But again, the presentation is about that surface knowledge requiring for our principles exam. We went on to look at two statements that again appear in our exam. Resistance is proportional to length and resistance is inversely proportional to cross-sectional area. So if I have a cable with a resistance of 10 ohms and I double its length and remeasure its resistance, its new resistance will be 20 ohms. If I take the same cable with a resistance of 10 ohms and halve its length and remeasure its resistance, its new resistance is 5 ohms. They are proportional. Double it, double the size of resistance, half the size of resistance. We also looked at the area of the conductor. If we were to double the area of a conductor, it has the inverse proportion. In other words, we halve its resistance. So the same cable with a resistance of 10 ohms has its cross-sectional area doubled. Sometimes the exam says double its size. Its new resistance would be 5 ohms. We went on to look at permanent magnets and magnetic fields, and they have some rules. These rules could come up as exam questions. Lines of magnetic flux flow from north to south. They take the shortest possible route from north to south. They cannot be broken, only reshaped. And magnetic flux is measured in the Weber, and flux density is measured in the Tesla, which adds 2 more SI units to my first presentation. We went on to say that opposite poles of a permanent magnet attract, so a north will attract a south, and like poles, so 2 souths, would repel each other. We also stated some of the enemies of magnets. Magnetic fields can be lost or interfered with by stronger magnets, by vibration, or by vast amounts of heat can affect a permanent magnet or a magnetic field. We then went on to look at electromagnets, and we said that all current carrying conductors create around them a magnetic field. That magnetic field can be increased by increasing the amount of current being passed through the conductor. So larger conductors carrying more current will create a stronger magnetic field around them. We can give that magnetic field direction if we know which way the current is flowing. And we said if the current was flowing away from us, it was like looking at the back of a dart that we'd let out of our hand and we'd thrown at a board. We saw the cross on the back of the dart. Therefore, the current was flowing away from us. It creates a magnetic field around the conductor that rotates in a clockwise direction. Likewise, if the current was coming towards us or somebody had thrown a dart at us, the first thing coming towards us was a dot or a point, and that was used on a drawing to suggest that the current was coming towards us, and current coming towards us would create a rotating magnetic field around the conductor that goes in an anti-clockwise direction. We then went on and looked at if we had two current carrying conductors placed side by side, carrying current in differing directions, that the two conductors would repel or be pushed apart. Where we had two conductors side by side carrying current in the same direction, the two conductors would be pulled together. We then looked at how the current carrying conductor that creates a magnetic field around it can be utilised. In other words, if we curled that current carrying conductor into a coil, we saw that the magnetic field created around it greatly increased in strength. This is the basic principles of a solenoid. A solenoid is really just a coil of cable carrying current, creating an electromagnetic field. That magnetic field can be polarised by using the right-hand grip rule, where on the right hand the fingers are the current, which direction it goes, and the thumb points to the north pole. So if we've gone over the top with our current wrapped around that way, or underneath, we see how we can polarise either end of the coil to be north, the opposite one being south. Often in exams, they will draw a picture and ask you to polarise it. In other words, tell me which side is north using the right-hand grip rule. Next, we went on to look at force on a conductor in a magnetic field. So in other words, we have a current carrying conductor creating a magnetic field placed within a magnetic field, a permanent magnetic field set up by a north and south pole, and the interaction between the two. This uses Fleming's left-hand rule in order to use three fingers, one for direction or movement of the conductor that's been placed into magnetic field, one finger for the polarisation of the permanent magnetic field from north to south, and one being the direction of the current within the conductor itself. And by using Fleming's left-hand rule, you can work out whether the conductor's being thrown up and out of the magnetic field or down and out of the magnetic field. Again, questions in our exam like to use Fleming's left-hand rule. In recent history, they've told you which hand to use when showing you a current carrying conductor placed in a magnetic field, being Fleming's left-hand rule. On Fleming's left-hand rule, it's also worth remembering what each of the fingers is named or doing. So in other words, the thumb is the direction. The index finger from knuckle north to south is obviously the magnetic field. So direction, magnetic field, and the finger being for the current, the direction of the current. So whether it be away or towards you. So just remembering the three fingers and what they are doing or what they're named within Fleming's left-hand rule could also get us some marks in the exam. On the back of Fleming's left-hand rule, we went on to look at Fleming's right-hand rule. This time, we've got a conductor being placed in a magnetic field, not a current carrying conductor, a conductor. And we're going to induce an EMF into that conductor. So in other words, the basic principles of generation. And sometimes they call the Fleming's right-hand rule, not necessarily just the right-hand rule, but the generator, as in the right-hand rule. So when you're reading a question in the exam that says a conductor is being placed in a magnetic field in order to generate an EMF, which hand will be used? It will be Fleming's right-hand rule. And again, within this section, we may only be required to identify the three fingers on Fleming's right-hand rule, the thumb being movement or motion, the index finger being knuckle north to south being the magnetic field, and then the final finger being the induced EMF into the conductor itself. So not necessarily going to be using Fleming's right-hand rule. However, the exam has had questions before where it asks you to use the right-hand rule, but again, indicates to you that's the hand you should be using. But sometimes it's simply just a labelling of the fingers, motion or movement, magnetic field from north to south, and induced EMF on the right-hand rule. Next thing we looked at was single loop alternators. In other words, a conductor being rotated in a magnetic field, and whether we could produce AC or DC from rotating that conductor within a magnetic field. And we saw if we connected that single loop of wire to slip rings and rotated it 360 degrees through a magnetic field, we saw how we produced a AC waveform, in other words, a sine wave. One complete revolution of 360 degrees will give you a sine wave with a peak in the positive half of the cycle and a peak in the negative half of the cycle. One complete revolution is also called a period. We also looked at rotating a single conductor through a magnetic field when it was connected to a commutator. In other words, it only took the positive half of the cycle each time as it was rotated through the magnetic field. And this is the basic principles of producing DC or direct current. Again, this is only a whistle-stop tour of this section of principles notes. Isn't the full underpinning knowledge. It's the surface knowledge required to enter the exam at that sort of basic level where we're trying to progress from these video presentations in order to get a distinction. But we're going in there with that surface knowledge that we understand the basic principles of magnetism, and the basic understanding of resistance and resistivity will allow us to pick up marks within this section. As always, I expect you to remember everything I've taught you in the classroom. I get every single question right, but this is the sort of minimum position that we should be in going into the exam with our knowledge levels. So this is part 4 of the Science and Principles recap. After looking at basic machines in the form of a loop of wire being rotated in a magnetic field connected to slip rings in order to produce AC, or a single loop of wire rotated in a magnetic field connected to a commutator in order to produce DC, we went on to look at frequency. Frequency is measured in hertz, therefore another SI unit that could appear in this exam, and the frequency in the UK is 50 hertz, or 50 cycles per second. We looked at how we could produce an AC waveform by rotating a conductor 360 degrees in a magnetic field placed between a north and south pole. A pair of poles, so the machine would have a north and south pole. We said the machine had a pair of poles, and if we rotated it 50 times in 1 second, we would produce a frequency of 50 hertz. We then looked at if we added a second pair of poles, so in other words another north and south, making the machine have 2 pairs of poles, so 2 souths and 2 norths, and we rotate the same coil of wire through the magnetic field, we had to rotate it half as fast in order to produce a 50 hertz cycle. We looked at the basic construction of a sinusoidal waveform, or a sine wave. We plotted it through 360 degrees, and we called this a period. The period has 2 peaks, one in the positive half of the cycle and one in the negative half of the cycle. We then discussed about our machines, where they'd be measuring current or voltage that we insert into a circuit that doesn't measure this AC waveform that peaks in a positive and negative half of the cycle, that it actually fixes itself on the measurement of the RMS value of the cycle. RMS is represented mathematically by 0.707. Therefore, if the peak value of voltage was 10 volts, the RMS, or the measured value from the machines that we would insert into circuit, would be 7.07 volts. So mini recap then, one AC waveform is a period. A period has 2 peaks. We measure the RMS value, which is 0.07 of the peak value. We know that in order to get a complete cycle, we need to rotate our conductor 360 degrees through the magnetic field. We went on to look at simple calculations to find either frequency or periodic time, in other words, a time for one cycle. We saw the formula was frequency equals number 1 divided by time, and that was periodic time, or the period, the one cycle time, in order to work out frequency. And then we could work out periodic time by time equals 1 divided by frequency. After those few calculations on frequency and periodic time, we moved on to a new subject. We looked at power. Power is measured in watts, and therefore can be measured in kilowatts, kilo being 1,000, or mega being megawatts, being 1,000,000 watts of electricity. So again, we've put in a few more units there that could come up in our exam. I've seen exam questions before where just ask how much is a kilo worth, how much is a mega worth. So kilo being 1,000, mega being million. A number of formulas are required to be remembered in power, but I set us the challenge of remembering just 3 and then using our maths to obviously rearrange those formulas. If we weren't looking for power, we were looking for one of the other elements within the construction of the formula. So the 3 formulas I expect us to remember are P for power equals I for current multiplied by V for voltage. The second one I expected us to remember was P for power equals I for current squared this time, multiplied by R for resistance. So power equals I squared R. And the third formula I needed us to remember was power, P for power equals V for voltage squared divided by resistance. So it gives us the 3 formulas I expect us to remember. P equals I times V, P equals I squared R, and P equals V squared over R. I'd love us in the exam to be working with all 3 formulas, rearranging them and finding missing elements. However, our default position is to remember the 3 formulas and what each of the letters stand for. It might be a case of just recognising the formula in the actual exam, not necessarily always working with it. Okay, these presentations are at the lower end of knowledge. The distinction candidates will be working with the formulas after remembering and rearranging them to find answers. We briefly looked at energy in the form of an energy meter, in other words, the electricity meter at home, and we said that energy is the kilowatt hours, and we went on to work out basic calculations to work out the kilowatt hours used by a consumer. We saw that a watt meter, in other words, to measure power, had two coils in it. One was measuring voltage and one was measuring current. And the voltage coil was a very high resistance and the current coil was a very low resistance. Again, these basic questions on a watt meter come up in the section on power and do not require a calculator and are worth remembering. After power, we went to look at transformers, and we said that basic constructions of transformers look pretty similar in the form of a primary winding and a secondary winding. I know an auto transformer is slightly different. So let's look at the basic construction of a transformer first. Primary side winding and a secondary side winding, they are not physically connected together. They are connected together by mutual inductance. In other words, the magnetic field set up by the primary side interacts with the secondary side, but not a physical interaction. This is a rising and collapsing magnetic field which will induce an EMF into the secondary winding. For our level 1 and level 2 calculations, we said that if a transformer had, say, 100 windings primary side and 100 volts, and 100 windings secondary side, it would have a secondary side or outgoing voltage of 100 volts. We didn't really look in any detail at the losses in transformers, which will be covered at level 3. We suggested the core, if there was one, because we can use air to have the magnetic field pass through air, but if we have a core in our transformer, we like to use a material that's easily magnetized, such as soft iron. We then went on to look at how voltage can be stepped up and down through the transformer. This is AC voltage, remember, and not DC. We cannot transform DC voltage, it's only AC voltage that can be transformed. Again, that's an exam question. We went on to see that if we had, say, 100 windings on the primary side and 100 volts, and we had only 50 windings on the secondary side, that we would have just 50 volts. Therefore, we would have stepped down the voltage onto the secondary side. Likewise, if we had 100 windings on the primary side and 100 volts and 200 windings on the secondary side side voltage would be 200 volts and we would have stepped up the voltage. We went on to do calculations to do with changing voltages in primary and secondary windings, and we used ratios to do so. We saw a very complicated formula, but we stuck with a ratio of primary to secondary side in order to work out whether we've gone up or down with the number of windings or up and down with the number of volts. The exception to this rule is current. Current works in the opposite. So in other words, if we'd stepped up the voltage, we would step down the current by the same ratio. So if a primary side has 100 turns and 100 volts and 10 amps, if our secondary side had 1,000 turns, 1,000 volts, it would only have 1 amp on the actual secondary side. So in other words, we've stepped up the voltage by 10 times. So we've gone from 100 to 1,000, but we've actually brought the current down by 10 times from 10 amps down to 1 amp. And we discussed the massive benefits with this, with the distribution systems. So in other words, we've got a maximum voltage in the UK of 400,000 volts or 400 kV being used on the supergrid, super high voltage, but therefore we've brought the current dramatically down, making the conductors on the supply authority side considerably smaller. We did go on and mention some of the losses in transformers, even though our calculations had perfect transformers with no losses. We said the core itself can have a loss in it, and that is an eddy current loss. And we said that we overcome this by cutting the core or slicing it into what we call laminations. So each individual slice is insulated from the other individual slice, and therefore making the core easily magnetized, might be soft iron, but very high resistance, making the actual eddy current that's induced into it considerably smaller than a core that wasn't laminated. We mentioned hysteresis and copper losses on the way through, but they won't appear in our level 1 or level 2 exam. We did suggest that not all transformers had a primary and secondary winding, that some transformers can be constructed of one winding, and we looked at an auto transformer, and we said sometimes these are used on the grid system, making them cheaper to construct. And we also looked at them in the form of little bell transformers that can be used domestically, so you can tap off the actual volts you need to drive your door entry system. We mentioned in this section SELV, separated extra low voltage. And we said this voltage range AC was up to a maximum of 50 volts, or up to in DC a maximum of 120 volts. We looked at how an SELV transformer has no outgoing connection to earth and therefore is electrically separated, which is a method of protecting against electric shock, as well as the voltage being no greater than 50 volts AC as well. We will go on in the classroom to look at SELV transformers in a later set of notes as well and applications for them. We also looked at isolating transformers in the form of a transformer that supplies a shaver socket in a bathroom. This could still be at 230 volts, but again has no connection to earth on the outgoing side. Therefore, the shaver inserted into the socket only has 2 pins. The earth pin is missing. The transformer that supplies the actual shaver socket itself is also an isolating transformer. Therefore, no connection to earth on the outgoing side. Therefore, no risk of shock on the outgoing side to earth. So just to recap then, basic constructions of a transformer looks like a primary and secondary winding. These windings are insulated, usually wrapped around something that's easily magnetized, such as soft iron. They are not physically connected together, only connected together through mutual inductance. In other words, the rising and collapsing magnetic field that's induced from the primary side is picked up by the secondary side. Calculations on transformers work on ratios. Transformers can be cooled in 2 main ways, either by oil or by air. We said that the loss that the exam may mention is the eddy current loss. This is overcome or greatly reduced by laminating the core of the transformer, in other words, slicing it up and insulating each slice from each other, making it highly resistive, but still. After completing transformers, we went on to quickly look at basic fluorescent lighting circuits. Very little knowledge here to move forward to our exam, and certainly no calculations. It's just remembering the basic construction and really what the inductor's doing. The inductor can also be called a choke or a ballast within questions in this section. When the fluorescent lighting circuit is completed by closing the switch at the door, the circuit is made through the ballast itself. Remember, it can be called a choke or inductor. Circuit then goes through to the starter. The starter blades are in the open position. The heat is generated in the neon gas in the starter, causing the blades within there to close. Circuit is completed round to the other side of the tube. What happens then is the gas starts to cool. It opens the blades within the starter, causing the massive back EMF developed by the choke to be dropped across the very low resistive tube, causing the tube to ignite or light. The questions in the exam are more based on what the ballast is doing in circuit. So on starting up, the ballast is there to develop the large back EMF that drops across the low resistance tube. When the lamp is illuminated, the job of the ballast then is to be a current limiting resistor in circuit. Other questions in this section will be about the capacitors. There's 2 capacitors normally in a fluorescent lighting circuit. There is one in parallel with the supply, which is there for power factor correction, which we went on to look at in a small set of notes at the very end on AC theory. Another capacitor is built within the actual starter to limit radio suppressive interference, that crackling effect when the fluorescent lighting circuit is turned on that causes interference in radios, etc. So after fluorescent light fittings, we went on to look at AC theory. I'm going to pare this down quite a lot in this presentation. We took ourselves to a painful position in the classroom notes. Our exam at level 1 and level 2 doesn't require anything near what those notes took us to. Those notes were introducing really AC theory for level 3. So this is the minimum requirement of recall knowledge within this section on AC theory. We said in an AC circuit that is purely resistive, the current and voltage are in phase. We said in an AC circuit that is purely inductive, the current will lag the voltage by 90 degrees. And finally, in a purely capacitive AC circuit, we said the current will lead the voltage by 90 degrees. These 3 are regularly asked in multi-choice questions, especially at level 2, and need remembering. Resistive in phase, inductive lags by 90 degrees, capacitive leads by 90 degrees. We went on to look at the impedance triangle, and we said that AC, current being passed through a circuit, now offers impedance made up of the resistance and the inductive reactance elements of the circuit. So we went on to use the impedance triangle, so 3 sides of a triangle, and we did the A squared, B squared and C squared. So we looked at a little bit of trigonometry in order to start working out the impedance of a circuit. Again, I'm not looking for us to remember necessarily the maths part of it here. I need us to remember that the opposition to current flow in a circuit with AC in it is impedance, represented by the letter Z, and impedance is also measured in ohms, as is resistance, being the opposition to current flow. After working with trigonometry to find any one of the 3 missing sides, of the calculations set out in my notes, again not necessarily required for this presentation, we went on to look at power factor correction. Again, we need to remember that a power factor will be between a number between 0 and 1. If the power factor was 1, we said that the power factor is in unity. In other words, true power and apparent power are the same. We don't like to leave circuits at unity, at 1. We like to have a slightly lagging power factor, so our number will be less than 1 between that and 0. So often we hear power factors of 0.85 or 0.9 lagging as a power factor. We went on to work out simple calculations for power factor as well. We worked out our power factor in 3 ways. We did true power over apparent power. We did kilowatts or watts over kVA or VA. And we did resistance over impedance. Again, it would be lovely to remember all 3, but worst case position or worst case scenario is to remember power factor will be a number between 1 and 0. Unity is at 1. We like to leave our lagging power factor of say 0.8, 0.9, etc. After the misery of AC theory, which I made last about 2.5 minutes in this presentation and last just one whole 3-hour evening, we went on to look at 3-phase systems. 3-phase generation of supply has our 3 lines being generated 120 degrees apart, which mathematically is 1.732 and was used in the section on star and delta connected loads. Again, if we can remember 120 degrees apart, it's another question we can get right in this section on 3-phase systems. We looked at delta connected loads not having a neutral, just simply comprise of 3 lines. We looked at a star connected load where a neutral was introduced. The reason the neutral was introduced is so we could have a single phase supply of any one line and neutral, giving us a single phase supply, where delta didn't, because delta only had 3 lines and you couldn't generate a single phase supply from it. We then went on to look at the section on star and delta connected loads and do the mathematical relationships between line and phase currents and voltages. Again, a trickier section that requires calculations, but some bits can be remembered without the use of a calculator. In a delta connected load, the line and phase voltages are equal. In a delta connected load, the currents are out by 1.732. If you knew the line current, between any 2 lines the current, the phase current would be the line current divided by 1.732. If you had the phase current and you wanted to find the line current, you'd multiply the phase current by 1.732. In a star connected load, we've introduced a neutral, so this time the line voltages and phase voltages are out by 1.732. But in a star connected load, what is common, the line current and phase current are both the same. If you knew the line voltage in a star connected load and you divided it by 1.732, you would get the phase voltage. If you knew the phase voltage of a star connected load and multiplied it by 1.732, you would get the line voltage. So let's recap. Easy things to remember. Delta connected load has no neutral, therefore the line and phase voltages are equal. The currents are out by 1.732. Star connected load. In a star connected load, a neutral is introduced. Therefore, the voltages are out by 1.732, but the currents in a star connected load are the same in all parts. I recommend you have your set of notes in front of you as you've just looked through this presentation, or as you go through it the second time, get your notes out for the presentation as you run through it. It's not as simple as some of the other ones, just to remember some of those facts. The notes will help jog your memory.